2010 paper 1 question 16. So this question is about forced oscillation with damping. So in the forced oscillation, first you have a free oscillation, a free oscillator. In this case, is the spring mass is free, but it's however is driven by another oscillator. So we say this is the driving oscillator, and this is the driven oscillation or forced oscillation. Okay, then damping means this forced oscillation is in the dissipative medium. Dissipative means energy loss. Okay, energy loss. So this is the setting, and for damping you have three types. You have light or under damped, critical, heavy or over damped. So you can imagine the following three pictures. Light damping is just a spring mass in air resistance. Okay, very minimum damping. The spring mass can oscillate for quite a long time. Okay. For critical damping, it is in a viscous liquid. For heavy damping means more damping. That means even very viscous liquid. Okay, very viscous liquid. So when you make displacement, the mass will slowly go back to equilibrium point. It is slowed down because of the viscosity. And then for very viscous liquid, it will become even slower. So it will take a very long time, eventually go back to zero. Okay, because very viscous means very slow. Okay. The question asking about the graph of amplitude versus frequency. Amplitude is amplitude for forced oscillation. Okay, frequency is the driving frequency. Okay, like this is a driving oscillator, and this is the forced oscillator. Okay, so the reference line, you must have this reference in your mind that this is the natural frequency of the system, and the orange color is with very little damping, which is described a real world scenario. If there's no damping in an ideal world, then this thing should go to very high. That means you expect an infinity amplitude at the natural frequency. However, this is not realistic. So we will say the reference is like a very little damping here. Okay. Then the question say that the spring mass system is then attached a piece of cardboard for what? To increase damping. Okay, but the cardboard is still very fine damping because the cardboard is just like to collect more air resistance. Okay, it's still far from viscous liquid. So from your everyday experience, you can expect this thing will still up down, and then eventually disappear, which means it is still in this category of under damping or light damping. So the result is the amplitude will be suppressed, meaning now the curve will become lower amplitude. Why lower amplitude? Because energy is lost. We just say damping means energy loss, so that's why low amplitude. And then the resonant frequency become lower frequency because in a damping medium, it's like there's a dragging force. As a result, you have to oscillate at a lower frequency. And just pay attention, with increased damping, the whole thing is suppressed, but there should be under the envelope. Let's call this orange color envelope. The red color should fall below the envelope, meaning for any point it should be reduced amplitude. Okay, that's the point. And you should also notice that they start from non-zero at zero frequency. the force oscillation is non-zero. Okay, and then going up to reach the peak, and then going down, eventually they will approach zero. Okay, finally, what does this mean? A non-zero amplitude when frequency is 0 Hz. It simply means as your frequency go to lower and lower frequency, your amplitude approach a non-zero value. That's all. Okay, for example, this can be 0.00001 Hz. Then the value is A. Or it can be 0.001 Hz. It is still A. Or it can be 0.1 Hz. It is still A. Okay? So the answer is D.